All right, so let's go through the warm-up. So find a vector D, or a number D. Find a number D such that these two vectors are perpendicular. All right, so we want to show they're perpendicular. We know that if they are perpendicular, then what's going to be true about their dot product? Dot product should be 0. So we're going to take the dot product of V and U. We take that dot product, I will get D times D, or D squared, plus 2 times 1, which is 2, plus negative 3 times D, that's minus 3D. And the question is, when is that thing equal to 0? So we're just kind of in that same situation that we've been in. We've been calculating determinants or eigenvalues. We're trying to find out when this quadratic thing is equal to 0. So I'll just reorganize this thing to be D squared minus 3D plus 2 is equal to 0. And we'll see if we can find some roots. It looks like I should say D minus 2 and D minus 1 equals 0. It should be right? We can double check here by multiplying it back out. Of course, if you can't see that factorization, then plug it in the quadratic formula or plug it in your calculator. And when we do that, we see that when D is equal to 2 or D is equal to 1 would be our solutions. So those are the two values that make these two vectors perpendicular. Any questions about that one? Once again, just emphasizing the fact that they're perpendicular when the dot product is equal to 0. All right, the next is find a vector that points in the same direction as this vector, 3, 0, 4, but has a length of 1. So they're asking for the unit vector. We're going to be a little bit careful because last time in class I talked about we have a vector V, and then we might ask what is its unit vector. And that's the notation that we use in Calculus 2, because I teach calculus a lot, and that textbook uses this. Unfortunately, this book is going to use the same notation for something totally different, called the projection that we're going to talk about today. All right, so we'll try to stick with what the book says. They don't have a specific notation for a unit vector. They just write unit vector by its definition, which is this thing. It says take that vector and divide it by its length. So in our case, we have 3, 0, 4. So to find the unit vector, it's just going to be that vector, 3, 0, 4, but divided by its length, or multiplied by 1 over its length. Its length is going to be the square root of 3 squared plus 0 squared plus 4 squared. 3 squared is 9, 4 squared is 16, together that's 25, and the square root of 25 is 5. So this is what we have there. So this would be the unit vector. Any questions about those two problems from the warm-up? All right. Plan for today. Lots of stuff today. First, exams have been returned, so you can look through those. I can spend a whole lot of time looking through those class today because I passed out the keys to them as well. So I want you to kind of take them home, look through them, see if you have any questions about the key. And then you can bring kind of more prepared questions to class for tomorrow. Okay, so I will take questions on our, one I would suggest go through, check the scoring, right? The number of points is indicated on the questions, so make sure you look through, see, if you feel like you need partial credit and I didn't give it to you and you feel like you did enough work there, feel free to come to my office hours, we'll talk about it and go through it. I have no problems doing that at all. The worst I can say is, no partial credit there. Which I might, but never hurts to ask. So look through the key, see if I added up the points correctly, make sure the number on the back matches the total number wrong on the front. Look through the key. If you have questions about the true and false, I'll be happy to talk about those today. Otherwise, any kind of questions that pop out at you, I'm happy to answer. Take a second to look through that. I also returned the review quiz, so I did kind of grade that kind of loosely here. I went through it and I kind of broke down the points. It was about worth 40 points. I didn't want to weight it to be 40 when I put it into the thing on Canvas, so I wanted to scale that down to a score of 20. So what I did is I took the number of things you got wrong and divided it by 2 and dropped whatever was left if there was a remainder. and subtracted that, so your score will be weird, right? So on the back, if it says, you might say -5, and then you have an 18 out of 20, and you're like, how did I get that? Well, I took the -5, divided by 2 to get 2.5, dropped the half, and it was -2 out of 20. Okay. Okay, questions? Any questions? All right. I'll have another kind of question session at the beginning of class tomorrow, so make sure you look through that exam. A lot of this content is going to be on the final, so make sure you understand why you got problems wrong on this exam. Make sure you go through it. All right, the other topics for today are, to finish our discussion, we kind of finished with quickly about orthogonal complements. After that, we're going to get into the projection, creating orthogonal/orthonormal sets, or bases as well, using the Gram-Schmidt process. We also might have a chance to talk about orthogonal or orthonormal matrices. That might be pushing it. We'll see how far we get today. All right. So we return the exams. And just kind of a reminder of some of the definitions that we kind of closed with. The last topic we were talking about was orthogonal sets and the orthogonal complement. So I just want to kind of redefine those real quick. I wrote them a little bit differently this time, maybe easier, maybe not. So X is orthogonal to a set. We know that X is orthogonal to another vector if their dot product is equal to 0. What does it mean to be orthogonal to a set? A set with a bunch of stuff in it, a bunch of vectors in it. Well, it's orthogonal to that set if and only if X is orthogonal to all of the vectors in that set. So it's orthogonal to V1, V2, all of them. So that wasn't too bad. This orthogonal complement, V perp, is a little trickier. This is a set of vectors. It's the set of all the x's that are orthogonal to V. And so we show that X is orthogonal to V if it's orthogonal to all of the elements in V. If I gather up all those things that are orthogonal to V, that makes up V perp. We did a little example last time where we talked about V being equal to the set of all vectors such that X is equal to some number times 1, 0, 0. Okay. All the multiples of this vector, I think on that line. Talked last time all about V perp would then be all the vectors in this plane. All those vectors, any linear combination of maybe this vector and this vector, any of those things are perpendicular to all of the vectors on that line. Another way to maybe see that would be to say if I have this vector here coming out of my table, I was looking at this as a space, all of the multiples of this vector, so anything along this kind of line here. All the vectors that lie in this tabletop will be a set of all vectors perpendicular to this vector. Any vector I put in this tabletop is going to be perpendicular to this vector coming out. Not only this vector, but 2 times this vector and 3 times this vector. All of them. Now, one of the reasons we look at this definition is because we have a fancy theorem here. It says the row space of A, the orthogonal complement to the row space of A, is equal to the null space of A. And the orthogonal complement of the column space of A is equal to the null space of A transpose. And it's like, huh? You can look at that and say, what does that mean? We're not actually going to use this a whole lot. For us, it's really just, we can state this theorem at this time, and it's an important theorem because it allows us to generate important stuff in further classes. So we're not going to work on it a whole lot. One thing I do want to talk about is I want to sketch a proof to it. Not because it's necessarily important that we prove this one, but it brings up a lot of important pieces, a lot of concepts of proof. What this is really saying here is we have these two sets and they're equal. This is over here is a set of vectors. It's a set of all the vectors that are perpendicular to the row space of A. And we already know the null space of A is a subspace, so it's a collection of vectors that satisfy certain properties. How do we show that two sets are equal? That's kind of the first question. I don't know if we've ever done that before, right? So to show that two sets are equal, right, so in other words, if I wanted to show that two sets, A and B, for instance, are equal, this is how I do this. I have to show that I need to show that if I have some element in A, then X must also be in B. In other words, all of the stuff in A has to be in B. But not only that, but if I have some element of B, then V has to be in A. All right, so I show that they're subsets of each other. This is a subset of this, and this is also a subset of this. If I show both of those things are true, then they must be equal. That's why I'm showing that they contain the same stuff. So in this case specifically, we would have to show so we need to show that 1, if X is in the row space of A perp, then X is in the null space of A. And then 2, if X is in the null space of A, then X is in the row space of A perp. Okay, so we're going to show one of these, and then in that process, you kind of see how we would show the other one. Once again, it's more about what we're doing, not so much that this is the proof, but the key concepts. And one of the key concepts is to show two sets are equal, we have to show this process. If X is in one, then it's in the other. If it's in the other, then it's in the one. Any questions about that start? Okay, as when most proofs in linear algebra, it's just about the definitions. If you're solid on the definitions, the proof will flow pretty easily. Okay. So what does it mean for X to be in the row space of A perp? First of all, what's the row space? I don't think we ever even introduced that. Anyone want to take a guess what the row space is?
Just like the column space that was like this.
Absolutely. The column space is just the span of the columns. Row space is the span of the rows. All right, so if I have some matrix, I'm going to call the rows row 1, row 2, row 3, dot, 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 whatever it's going to be. Then I'll say V is in the row space if V is some linear combination of the rows. Plus C2R2. I think to myself enough room here. Plus dot, 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 plus CNRN. Right, it's a linear combination of the rows. So X is in row perp. So X is in the row space of A perp if X is perpendicular to any of these V's. It's perpendicular to this thing for all of the C1, C2, Cn's, all the possible linear combinations of these things. If X is always perpendicular to that, then it's in the row space of A perp. Perpendicular to all of the V's, we'll say, like that. What does it mean for those to be perpendicular? It means that X dot V, these should all be vectors here, X dot V should be equal to what? 0. So this thing should be equal to 0, not the 0 vector, but 0. So now I'm going to take X dot V. So X dot, well, this is V, C1R1 plus C2R2 plus dot, 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 plus CNRN. And now I have some properties about dot products. So this is C1 x vector dot R1 plus C2 x dot R2 dot 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 plus Cn x dot Rn. So it's kind of like I'm distributing this thing. I have those properties for dot product. Dot product of the sum of the dot products, and I can factor each of the scalars out of each one of these. So I have this expression. And this is supposed to be equal to 0. Okay. Now not only is it supposed to be equal to 0, but it's supposed to be equal to 0 for any C1, C2 through Cn. So it's not like we're saying, okay, this is equal to 0, and maybe if I take 2 of these and then negative 2 of these, this is going to work out to be 0. But this is 0 no matter what the C's are. So it doesn't matter what the C's are. What does that tell us about these other values? That this thing is always equal to 0. All these dot products are 0. Each one of these has to be 0. Okay? Because this is true for any values of C. Right? So 2 of these, negative 4 of these, 6 of these, doesn't matter. No matter what combination of C values we pick, it's always equal to 0. Well, that's only going to work if each one of these dot products is equal to 0. So what we're finding now is that all of these dot products are equal to 0. So x dot R1 is equal to 0. X dot R2 is equal to 0. X dot R3 is equal to 0, so on and so forth. When I think about making a big list of stuff like that, like this, I say, wait a second, this over here is actually just the definition of matrix multiplication. When I do that matrix multiplication, if I do that process where I'm taking this column times the first row, and I'm adding all the products, really that's just the dot product definition. So this, when I do this multiplication, it's x dotted with the first row, dotted with the second row, dotted with the third row. That's how I do that multiplication. So this tells me that ax must equal 0, which tells me that x is what? Lives where? If ax equals 0, then x is in what? It's the null space. So now I've shown that x has to be in the null space. So starting with x being in the row space of a perp, we've now shown that x is in the null space. And all those steps are just equalities, so that means I can go back and forth. So now I just start where if x is in the null space, and this is true, this would be true, and this is true, and I work my way back up. And that shows the other direction. Okay, so the reason I went through this proof, I know you guys love proofs. I can just see the excitement bubbling up in all of your eyes. But the reason we took a little time to go through it is for 2 reasons. One, to show that 2 sets are equal, we have to show this is true. That's an important concept because you show 2 sets are equal quite a bit in a lot of different areas. So that's a good process. The other thing is this idea of distributing the dot product. Because we know we'll have a basis, and so therefore any element, if V is in the row space, I can write it as a linear combination of its basis vectors. And then if I want a dot product it with something, I kind of distribute that dot product. That's also a common process of representing something as a linear combination of its basis, and then taking the dot product of that linear combination. So you'll see those 2 actions a lot. Okay. That's all I'm going to say about the orthogonal complements for now. All right, so now we're going to get into 6.2, 6.3, and 6.4. The next 3 sections are really going to revolve around the idea of orthogonal basis. So we want to do a couple things. One, we want to define it, what we're trying to find here, an orthogonal basis. Then we have to find a way to calculate it, to take a basis and generate an orthogonal basis. And we want to use it. What's the purpose of finding an orthogonal basis? And those are really the 3 big ideas in the next 3 sections. So we'll start off with some definitions, and I guess love definitions, almost as much as proofs. But these definitions aren't going to be too bad. So we're going to start off by defining what an orthogonal set is. An orthogonal set is a set of vectors that are orthogonal. All right, it's not a complicated definition, right? It's a set of vectors. It's a set of vectors that are all orthogonal to each other. Just what you would expect from that definition, right? What's an orthogonal set? It's a set of vectors that are orthogonal. From there, we're going to define an orthogonal basis. Anybody want to take a stab at this one? Orthogonal basis. Anybody?
Orthogonal set is also a basis.
Bingo, right? It's a basis and it's also orthogonal. Right, so pretty straightforward definitions here. It's a basis that is also an orthogonal set. All right, let's take it to the next level. An orthonormal basis. It's actually not too much worse here. When we normalize something, we're just taking the length out of it. We're kind of standardizing the magnitude or the size of something when we normalize it. So when we normalize a basis, we have an orthogonal basis that we're kind of generating now. One could be really long, one could be really short, and they could still be perpendicular to each other. Let's take all that variation of length out of there. Let's make them all the length of 1. That's all we do here. We're normalizing the basis vectors. So an orthonormal basis is just going to be an orthogonal basis where all the vectors have length 1, so therefore all the vectors are vectors of length 1 are also called unit vectors. Orthogonal basis of unit vectors. We've worked with these before. Anybody give me an orthogonal basis of unit vectors for R3?
JK.
1, 0, 0, 0, 1, 0, 0, 0, 1. They're all orthogonal. Look at the dot products. If I take the dot product of these two, I get 0 plus 0 plus 0. If I do have any of them, I'm going to get 0. These are all orthogonal. We know that. We've seen the coordinate system. They're all perpendicular to each other. They all also have length 1. They're all, of course, a basis because they're linearly dependent and they span R3. So we like these things. We like these orthonormal bases. These are easy to work with. All right. What if we don't have them? How do we calculate them? That's the next step here. To calculate them, we're going to use the idea of a projection. Basically, it's going to look like this. I'm going to give you a quick overview of all this stuff, and then we're going to go into details later. But it basically works like this. If I have these two vectors, these could be a basis for R2, but I want them to be an orthogonal basis. So what I'm going to do is I'm going to use a shadow, a projection. I'm going to look at how this thing kind of casts a shadow directly down into the other vector. So if I have the vector u, I have the vector v, I'm going to cast its shadow down here and call the resulting vector that looks just like v, but it's a little bit shorter, the size is now appropriate. I'm going to call that vector the projection of u onto v. We're projecting u down. It's like this image projects an image onto my screen, and if I hold my vector up here, it's going to cast a shadow. So this would be u. This back here would be the projection of arm onto screen. Okay? And when we find that vector, this is pretty nice because I'm going to call that vector, here's their notation here, u with a little hat symbol, that's the projection. And if I have that, I can find the vector I want. This is really the vector I want because I can see that's perpendicular to v. And I can just find that by taking u minus my projection. And what I'm left with is v and this thing, which looks like this. And hooray, I've got my perpendicular vectors. That's the general process here. I'm going to calculate a projection, and I'm going to take a difference of two vectors to find this nice perpendicular group. And then what are we going to use it for, this last piece? Two things. First thing I'm going to use it for is, I can see here that the projection of u onto v is the closest vector on the line that is v. So if I look at a space with a v, all the different vectors along this line, all those vectors, this vector is what I would call the vector that's closest to u. Right? It's closer to u than maybe this vector. This vector doesn't look like u at all. This one's the closest to u. That's how we kind of describe it. We'll see that in kind of other areas that will make more sense possibly. So it's the closest vector to u in the line. So the projection will talk about closeness. But also this is going to give us a new factorization. We're going to be able to get a new factorization for this. A new factorization. A equal to Q times R. Now, how is it going to do this? Well, we've seen a factorization before. What was the other factorization that we've worked with so far? Worked with a couple, actually. Somebody give me some other factorizations. Absolutely. P, D, P inverse. That's actually what I was looking for. LU is also a decomposition, but we won't talk about it right now. So what is P, D, P inverse? It's basically rewriting A in terms of a better basis. What was the basis we used here? Eigenvectors. The eigenvectors are basis. We change the basis, we do an operation, change the basis back. The basis has everything to do with these eigenvectors. This is also going to be a basis-based change. Here, here P was a matrix whose columns were those eigenvectors. That's why we kind of saw there was a change of basis to the eigenvectors. Q is also going to have special columns. Here it's going to be an orthonormal basis. That's why this one's going to be special, because its columns are going to be an orthonormal basis for our space. So it's also going to be working in a better basis. All right. So that's kind of the quick overview of what we're going to do here. Now let's get into the details. Another way to maybe approach that overview is we want to answer these two questions. The first question, maybe I'll write this a little differently here. I have these three vectors, and they form a basis for our three. But I would rather have an orthogonal basis. Orthogonal basis. So what we're going to learn to do is say, okay, I'm going to project, find that vector, find this vector, and that will give me a perpendicular one. And then later I'm going to project this one down, find this vector, find this vector, and I'll find this vector. And I will have an orthogonal basis instead of my regular basis. And the next question is, if I have this vector 2, 2, 3, that's this vector right here, can I find the closest vector to this vector in the plane? We kind of know how to do that. We would say, this is probably the closest vector. And we're going to formalize that idea. Both these ideas are going to involve the projection. So what is the projection and how do we calculate it? Okay, so along this route we are going to recall something we talked about just a little bit. In R2 and R3, U dot V, we know how to calculate in terms of a vector, that algebraic definition. But there's also a geometric definition in R2 and R3 that looks like magnitude of U, magnitude of V, times the cosine of the angle in between. It's the other definition of the dot product in R2 and R3. And the reason I like this definition is because it really tells us what the dot product does. It tells us how well these two vectors are aligned. Right, if we think about the values here, U is going to be some number, and V is going to be some number. But that cosine value, depending on the two vectors, is going to change. What's the biggest possible value for cosine theta? 1. Right? It doesn't get any bigger than 1. What's the smallest value in magnitude? Right, not with a sign, but the smallest value in magnitude that it can possibly be. 0. And so when is this the biggest value? When theta is equal to 0. When these things are perfectly aligned, this gives the biggest value. When is it the smallest value in magnitude? It's when cosine is 90 degrees, it's perpendicular. So in some sense, this is measuring how well these two things are aligned. Okay, so that's like a side note. Now I want to find the projection of U onto V. We kind of described what it was. It was casting this shadow down onto this other vector. And so this becomes the projection. This is my projection vector. And so really to find this projection, I need to find out what the magnitude of the projection is. Because I already know its direction. What is its direction? V. So I'm going to rewrite this as whatever this length is supposed to be, and that's what I'm trying to find out, the right length here, times the direction. Well, the direction is just v divided by the length of v. It's the unit vector, essentially, right? Now, I just got to find this length. So to find this length, I'm going to use a little bit of trig here. I'm going to notice that when I cast this shadow, this projection, I'm going to create a little perpendicular triangle, or right triangle here. Inside of that right triangle, I know that cosine of theta is equal to what? Ooh, some trig in the morning. Yes. Cosine of theta is equal to, same old horse caught a horse taking oats away. Sorry, I know you guys do SOHCAHTOA, right? It's my little mnemonic here. So caught a horse, cosine is the adjacent over the hypotenuse. So, is that? So the adjacent side is the projection. So we're looking at the magnitude of the projection over the magnitude of the hypotenuse. Okay. Okay, so I'm going to multiply both those sides by the magnitude of u to get this thing. Cosine of theta equals u prime here. And now I'm going to do kind of a weird thing. I'm going to multiply both sides by the magnitude of v. When I multiply both sides by the magnitude of v, I say, wait a second, I know what that left-hand side is. That left-hand side looks familiar. What is it?
Dot product.
It's the dot product. So this turns out just to be u dot v. Remember, I'm trying to figure out what that magnitude thing is. I'm trying to find out what this thing is. So now I just have to solve for it. I divide through by the magnitude of v, and I get the magnitude of the projection is u dot v divided by the magnitude of v. And I like that expression. That expression makes a lot of sense to me. Because I know it's got to be related to the dot product, because somehow this projection is related to the alignment. Right? They're perfectly aligned, well, the projection is just the actual vector, right? It's just the length of the vector on v. And if they're not aligned at all, the projection should be the zero vector. I'm going to get nothing there. So that length is related to this. But it should not depend on the magnitude of v. Because think about it. Here's the projection of u onto this v. But what if I project it onto twice as long v? Would that change the projection? Doesn't change it at all. So somehow the length of v doesn't matter in this calculation, which is good. That's why we're dividing it out here. Because you could change v, you could change this length. Oh, you don't change this value. They kind of cancel each other out. So this definition makes sense to me. It's the alignment factored out with the length here. So now I'm going to plug this thing in here. I have u dot v over the magnitude of v, and then I have v over the magnitude of v. Well, that's really just magnitude of v squared. Ooh, now I'm getting excited. So close. But I can rewrite the magnitude of v squared also in terms of the dot product. What is the magnitude of v squared in terms of a dot product? V dot v. So this is the definition for the projection. The projection of u onto v is u dot v divided by v dot v times v. There's a lot of v's, u's, dots here. We have to make sure we understand what this thing is. The projection is a vector. It's this vector. This says take a number divided by a number times the vector. So we should get a scaled version of v. It's really easy to mess your u's and v's up. I encourage you to think about the picture. The result should be some number times v, because all we're doing is essentially scaling v to be the right size here, and be the projection. Okay. A lot of talking. Oh, so one other important thing here. So now I have this thing. It's easy enough for me to find this vector right here. U, it's just u minus the projection vector. Now, if I talk about the span of u and v, I'll talk about the span of u and v. Is that any different than the span of u and u, the projection of u? It's not, right? Because u hat there, the projection of u, and v, well, they're just multiples of each other. But if I take u, or u, this thing, plus u, I'm sorry, if I take this thing plus this thing, I get to u, or I can subtract them to get to this thing, which means that this vector is just really a linear combination of these other two. Which means it's also in this space. And so is there any difference between this span and the span of this and this? Also the same span. So this is also the same thing as the span of u minus u hat and u hat. Like that. Which means if I look at these two things, I'm not changing the span of my space, I'm just changing the basis I'm using. So this is just a new basis for the same space, but of course it's orthogonal. So I've generated an orthogonal basis for this. Okay. Now, time for you guys to try. There's the definition of projection. Let's calculate this thing. So first calculate that projection vector, and then use it to find u perp. So let me just define that real quick. They don't really use this in our textbook here, but in calculus you'll see this. They'll call this piece, they'll also call this as u parallel. It's the component of u that's parallel to v. And they'll also refer to this thing as u perp. It's the component of u that's perpendicular to v. So there's just other names for these two vectors. Questions about those names? All right. The piece of u that's parallel to v and the piece of u that's perpendicular to v. So go ahead and calculate this stuff. This will be one of the most important definitions you're going to need in chapter 6, because we're going to use it all the time. Will 100% be enough to exam? This lesson is kind of like the calculus approach. I'll give you a definition you need to calculate, but I want to show you the picture that describes that formula. You learned about the derivative. Hopefully, if you talk about the derivative, you've all seen this picture where we take this and we do a secant line. You go closer and closer, and you write up your limit definition. Same thing here. You have a formula for the projection, but if you can draw that picture, vector, vector, and work yourself through the the definition. You can always get back to there if you forget it. All right, but we have our definition. We have u dot v over v dot v times v. So I just take u dot v. U dot v is 0 plus 4 plus 6. V dot v is 0 plus 4 plus 1. If you don't know where any of those numbers come from, please, 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 please ask. Any questions? Okay, u dot v dot v times my vector v, 0, 2, 1. I'm just scaling v. Looks like I have 10 over 5 times v. It's just 2 times v, so it's just 0, 4, 1. So that vector is my projection vector. It's the projection of u onto v. Now to find u perp, it's just u minus the projection. Yep.
0, 4, 2.
Oh, thank you. Thank you. Thank you. 0, 4, 2. All right, now I just find this u perp by taking the difference of these two vectors. So I have u 1, 2, 6 minus 0, 4, 2. And it looks like I get 1, negative 2, 4. So I started with a u and a v. I calculated this vector u hat, and then I calculated this one, u minus u hat. And that result, when I'm done, this u perp thing should be perpendicular to v. Well, how do I test if these two things are perpendicular? I can always check by taking my dot product now. So I have 0 plus negative 4 plus positive 4. So I will get 0. So this is perpendicular to this. So I feel a little more confident. All right, any questions about that calculation? So when I messed that up, I was just going to test it at the end, perpendicularity. Okay. Any questions? Okay. So what about the projection onto a subspace? This is a little bit more complicated, but not too bad. We'll kind of sketch out the philosophy here, and then I'll give you the definition. Here's my vector v, 3, 2, 2. What I want to do is project this now not just onto a vector, but onto the plane. I want to do that because that result, that projection vector, should be the closest vector in the plane to this vector. But how do I project onto the plane? Well, I kind of know the answer in this case. Now, what do I want the answer to be here? What do I want this vector to be? If I cast the shadow on that vector straight down onto the plane, what do you think that vector would be? 3, 2, 3, 2, 0, we'll call it. Right? All I'm doing is getting rid of the z component. I'm sending it straight down. That's really what I want it to be. I want, I guess we should call it v here. V hat, the projection onto the plane, to be 3, 2, 3, 2, 0. Which is really 3, 0, 0 plus 0, 2, 0, which is really, when you think about it, the projection of my vector onto this thing, plus the projection of my vector onto this thing. Now we could practice that doing projections of just those standard basis vectors, but we don't really have time today. But the idea is this is kind of the process. What we're going to do is we're going to take an orthogonal basis in our plane and project onto the first vector and project on the second vector, and that sum is going to be projection onto space. So that's how I get this thing. And now how do I find this vector, which is another vector that I might want? Well, it's the same thing as before. It's just v minus the projection. It's kind of the same extension. I have to be a little bit careful here. Here's the definitions. if I have a set an orthogonal basis for some space W, that's a subspace of V. This is the plane. This is R3 in our example. So if I have an orthogonal basis for the plane, which is a subset of the R3, then the projection of V onto, for V in V, the projection of V onto W, and the projection from R3 onto the plane, is just the projection onto these basis vectors. I just project onto the orthogonal basis. Now we got a little bit careful because here, therefore, what's that perpendicular vector coming up? I said it's just that difference. But if this is a sum, don't forget we'll have to distribute that negative sign. So it will look like we're taking V minus all those projections. We have to distribute that negative sign. Okay, really this gives us all the tools we need now to generate orthogonal basis. We have a process for doing that called the Gram-Schmidt process. And so we can kind of, look at these definitions and say, oh, okay, that's what the definition is, but that really doesn't tell me what to do. Here is the process for doing this stuff. So we're going to sketch it right here. This is the Gram-Schmidt process to create an orthogonal basis from a regular basis. So here I have a basis U1, U2, U3 for R3. I want to find a new basis for R3. It has to have three basis vectors, V1, V2, V3. But I want those to be an orthogonal set. So I'm going to start with a vector. This is how we start. We say let V1 be U1. Right? I just need these V's to be orthogonal. I don't care which one I start with. So I'm just going to pick one, this one, and now I've got to find a vector that's perpendicular to this thing, orthogonal to U1. So I start off, I let this thing be V1. Then I got to use U2 to find my V2. I need to use this vector to find my next orthogonal vector. How am I going to do that? I'm going to project. And I'm going to find the projection of U2 onto V1. And then I'm going to take U2 minus that thing, the projection of U2 onto V1. And that should give me this vector. Now I draw it there as a displacement vector. But of course when I write it, it starts at the origin when I'm thinking about it as a space, so I'm basically finding this vector. Okay? So now I have two vectors that are orthogonal. And I got to find a third one. So now I have V1, I've calculated V2, this is going to be my V2. Now to find V3, I take the projection of U3 onto the space spanned by V1, V2. So then I look for the projection of U3 onto the span. Remember, I can project onto an orthogonal basis, but now I have an orthogonal basis. It's V1 and V2. And then I can use U3 minus this projection, and that will give me, essentially, it will give me, first I project down and get this vector, and then that difference gives me this vector. Once again, I'm drawing it as a displacement vector, but it's the same thing as this vector here. And that will be my V3. So V3 is going to be U3 minus the projection of U3 onto V1 minus the projection of U3 onto V2. So it's a process. This is for a three-dimensional space. If it was a five-dimensional space, five basis vectors, you would just keep doing this project or process. Find V1, go to V2. Find V3, find V4, so on and so forth. Okay? So here's all the mechanical steps to do it. Now we just got to practice. So tomorrow we're going to practice a whole bunch of this. And once we can generate this orthogonal basis, then all we have to do is put it into our factorization. And it's just, these are the columns of Q. Okay? That should finish up 6-4. Okay? So tomorrow we're going to review this, answer questions you have in the exam, finish the QR factorization, and that should be the bulk of the course. I'm really hoping to save most of Thursday for kind of a preparation. Each day, though, you should be looking at that giant final template thing that I sent out and kind of going through a little chunk out of it. It's 18 pages. You don't want to be cramming that in on Thursday night, find out you have a bunch of questions and not have time to ask. All right, so do it now, organize your questions, so on Thursday we can go through all your questions. All right, that's all I got for today.